Okay, so this is our second lecture on unsupervised learning. And then next week we will have two more. Next week we will do multi-dimensional scaling and also the EM algorithm, because it's often used in unsupervised learning to find groups. So what we're going to do today is we're going to look at clustering, and we're going to look at two things in the cluster. We're going to look at k-means, and we're going to look at hierarchical clustering, because these often are used together. So let's just recap what we're trying to do. We're trying to find subgroups or clusters in the data. And obviously, we've mentioned this a couple of times. I'll go into more detail when I do MDS. We keep talking about the idea of two objects being similar or different. So obviously, you often have either a dissimilarity coefficient or you have a metric. And next week, I'll remind you again exactly what these things are. So first of all, PCA is the one we looked at last time, and that finds a low-dimensional representation of the data. And the way they find that low-dimensional representation is they find linear combinations of the predictors that explain most of the variance. With clustering, what we're trying to do is find subgroups that are reasonably similar, they're homogeneous within the data. So we'll start with the k-means clustering. So the key idea of k-means is you start by saying, I want to split my data into k groups. So you pre-specify the number of groups that you want. How you choose the number of groups, often it's usually by the hierarchical clustering. G'day, Ross. So here's the setup. What we're going to do is we're going to pre-specify the number of groups, we'll call that k, and then each observation is going to be assigned to exactly one cluster. There is fuzzy clustering, which I'm not going to do today. Our idea is each observation will end up in one and only one cluster. So the notation we're going to do is to indicate these clusters. We'll call the clusters C, so there'll be C1 up to CK. And all that's going to do is give you the index of each observation. So first of all, if you think about it, you should find that your union of your C1 to CK should give you every observation, where each observation is labelled 1 to n. And the intersection of CK and another C dash K, that dash is associated with that K, it just looks in the wrong place, so I'll clean that, is equal to 5, so it's the empty set. So basically, your clustering has partitioned your indices that indicate each observation. So what that's basically saying in notation is every observation is definitely in at least one cluster, and it can't be in two clusters. There's no overlap. So that's great, but how do we get a good clustering? Most of them have a heuristic that says we want to minimize the within cluster variation. So you've got these clusters, you look at some measure of variability within each cluster, and you have to design how to measure that variability, and you want to minimize the total variability over all the clusters. So you're just going to try every possible cluster, for each of them measure the variability, and find the assignments that minimizes that clustering. And the fact that you can do that in a finite time is always quite impressive, because there's a lot of clusters. So the standard one that we often use, the within cluster variation, is the squared Euclidean distance. So all you do is you take every pair of observation in a cluster and you work out Tobin.
Disappointing you as always, John.
In what way? You came. It's amazing. Everyone else, I just go, morning, morning, there's Tobin! Just.
The excitement gets better and better as the semester goes on. I'm staying in it.
Oh, you're on my fucking CV, to be honest. Like, my teaching award, it just says, Tobin came to a lecture after week 3. And they just went, wow, that's seriously fucking awesome. We didn't know Tobin actually existed beyond week 3. He just like, this is week 3, and then boom, Tobin disappears and just turns up for an exam.
Yeah, it's usually like that.
You wouldn't want to have your resume become too long with all the lists of every lecture he appeared in, would you? Like,
yeah, no, I mean, it's just, I just named the 2 lectures he came
Exactly.
in. And he came in by mistake. I mean, he comes in, he looks and goes, oh shit, it's a lecture. I thought this was Netflix, I'm sorry. So the whole idea of this is you're going to take every pair of observations in the cluster and look at the Euclidean distance between them. In fact, the squared Euclidean distance, and then just add them up. Okay? And
John,
Yes.
what's the left sum for again?
so this is over, so each of your observations will have p predictors.
Yep.
So to get your Euclidean distance, you take the first pair of coefficients, take the difference, square them, plus the second. So the first sum gives you the Euclidean distance between 2 points. The sum of the other one, the I and I dash, is summing over all pair of points. And then you just normalize by the number of points. So when we put that in, this is what our heuristic we're trying to do. Just trying to minimize over all the clusters, all the pairwise distance within each cluster, where the pairwise distance is obtained by taking the squared difference between each predictor for each observation.
Sorry, Tom, why isn't it divided by the number of pairs rather than the number of points?
They've always just they've just done the number of things. It would be equivalent up to a mapping anyway, but they've always just decided just do it on the total number of pairs.
Yeah.
I think they see it as the total sum of squares per point, as
Okay.
opposed to per pair.
Yeah, okay.
Yeah. So how are we going to do this in a finite time? They've got a really nice technique. First of all, what you do is you assign each of your observations randomly to a cluster. Okay. Then what you do is you have this two-step process which you keep doing until there's no changing in assignment. The first thing you do is for each cluster you calculate the centroid. So the centroid is the mean vector. You take all the values for the first predictor of every point in that cluster, add them all up, divide by how many, go to the next one. So the centroid is your center of mass, your vector mean of all the points in that cluster. Then you go to each observation and go, which centroid is closest? I'll move you to that group. And you just keep doing that. So you just randomly unassign, then you say, here's my centroid. Once I've got my centroid, you look at a point and go, you go, I've got all these centroids, so I've got, say, 5 groups, there's 5 centroids, which is closer? I'm now in that group. Then you recalculate your centroids and you keep going. So why does it work? Well, let's look at this within cluster variance term, or sum of squares, or variability, if you want to call it. You can show, again, why would I show this when you have all that exam time spare to show these sort of things? You could show that this is equal to 2 times, you're taking every point, taking off the sample mean. Yeah? And by this, you can now start to see why you have that sort of just the number of points. If you redid that calculation, you can see that you can look at all the pairwise distances, but you can sort of just go, well, I'll just look at the distance to the mean, which is our centroid. Okay, so you've got that idea that I can rewrite this in terms of each point's distance from the centroid. But let's think about step A. When you calculate a centroid, you may not remember this, but your sample mean is the point that minimizes your sum of squares. So your centroid is designed to minimize, by default, it's the point that has the smallest variance to all the points within that cluster. So you know that by choosing a centroid, you've already minimized that. And then when I go and put a point to its nearest centroid, that is only going to improve the distance. So the second step where I move them is always going to either leave it the same or improve that term there. So this two-step process is always minimizing it. It's always saying when you calculate the centroid, you found the point that minimizes it. When you move a point, you're minimizing it. So let's show it. So what I've got here is some data that just simulates some points. We've got 2 clusters in this data. Altogether we have 50 points within each cluster, and I've just simulated the data by the x variable. has the values either 0 or 3 as its mean, and the x2 is just random normal with a mean of 0 and a variance of 1. Okay, so that gives me my data. Step 1, all I've done is I have given each cluster, I've just permuted the order. So I've randomly assigned them to a cluster. And I've set it as a factor. So here's my points at the moment. The colour indicates which cluster they've been assigned to. So what I'm going to do now is I'm going to write a function that will calculate the centroids. This is my function called getCentroids. It takes the data frame, it groups by cluster, and it calculates the mean of x1 and the mean of x2 for every point within that cluster, and it returns that. So I'm going to get 2 centroids, which in this case are these. So obviously the big blue circle is the centroid of the blue cluster and the red cluster. The next stage I'm going to do is I'm going to work out the distance from every point to both these centroids and move them to the one that's closest. So first of all, if you look at this, where you've got these left points, to some extent, every point to the left of the big left point is going to become blue, etc. But let's have a look at the code. So here's my code. It takes my data frame and my centroids. First of all, calculates the distance to the first centroid, the distance to the second centroid, and then finally puts your cluster just by saying which distance is smaller.
I love the title of your slide, John.
Thank you very much. I was hoping someone noticed that. Thank you very much. Be here all week. Try the veal. You get bored writing these. You might make that in your eye in step 2B. Don't tell you what's funny. Well, it was funny to me at the time.
Oh.
Did you seriously not get that?
Funny. That's funny.
If that's sarcastic, I'm going to beat you to death with a desk. And that wasn't sarcastic. So I've allocated and recalculated the centroids. And you just keep doing that until at any step you don't change your allocation. So here it is. I set my old cluster to equal to null, and then I basically say while they're not identical, which is the old allocation, new allocation, just do the step, print it out, reassign, keep going. And it took them points, and within, we've already done one step, within 3 steps, it's sorted. It's fast, it's remarkably fast, just the fact that we can rewrite it that way. So there it is, that's our final clustering. So let's have a look at a data set where we know what's happening. So we've got the iris. Remember the iris data set? This is a classic data set by Fisher, where he had looked at various measures of flower components for 3 different species of iris. So what I'm going to do is I'm just going to, so we can look at it visually, later we'll look at it with all the predictors. I'm just going to use the first 2 predictors, sepal length and sepal width. And I'm going to say, give me 3 means. I'm using 3 groups because I know there are 3 species within the data set. So how you do it, So there's a built-in function called k-means. And with the k-means, all you need to do is you give it the data. Obviously, there's no formula notation because this is unsupervised. There's no center response variable. And then you say how many groups you want. And when you actually look at this object, it returns a lot of information. So first it tells us, yes, I got 3 clusters. These are how many points I've got. 53 in the first group, 50, and then 47. The cluster mean, so it gives me the centroid. So group 1 has a centroid with a mean of sepal length of 5.7 and sepal width of 2.69. So you've got your 3 things. It also gives you how they're clustered. So this vector is very useful for actually assigning the clustering now. It gives you each of your within cluster for each of the groups. And there's lots of components you can get stuff out. You can get within sum of squares, between sum of squares, etc.
Are these species in order? So like they're all that one, then the next one, then the third?
I don't know off the top of my head.
Because if so, it looks like it did 2 very well, but then struggled a bit.
Yeah, and we'll see, we'll actually compare it to the truth later on.
Okay, sorry.
But no, it's good. So here's just a plot of the clustering, how it's done it, and also I've just put the centroids there so you can see them as well. So it's a quick way for looking whether 3 is right. I mean, we had context to decide on that. I mean, I haven't gone into detail here how you decide which cluster. Often I'll show you how I do hierarchical clustering and then use that to get. Some people use k-means directly, and they will just look at the total within some squares for different k's, and again look at a type of screed plot. But because we're going to do hierarchical clustering, we use that to decide on what k is going to be. So that leads into hierarchical clustering. So with hierarchical clustering, what we're trying to do is get a tree again. But it's slightly different. Remember before when we did carts, the whole idea of our tree was it was a decision tree. You start at the top and you made decisions to allocate things. What this has in this dendrogram is the nodes, the leaves, sorry, are going to be an individual observation. And the idea being that if 2 nodes get connected if they're close together. So if we go down to the very bottom, for example, right at the very far right, you've got observation 24 and observation 45. It is decided that them 2 are very, very similar. And as you go up, you start to connect them. In fact, the height tells you roughly how similar they are. And you can see that we start to see what we call clades. So if you start at the top and come down, you can see that roughly there's like a split to the right, and there's all these observations over on the right. You can call that a clade. And then over to the left, you've got that group, which you can call a clade. But you can actually go further down and you can decide where to cut this and cut it into clades.
So the shorter the vertical distance, the closer.
The closer 2 things are.
Yep.
Sort of like that line there. So how does it work? Well, there's different ways of doing it, but the one we're going to look at is called the bottom-up or the agglomerative clustering. So you start with all your observations, and you find the 2 observations that are closest together, and you join them. And then you keep doing that. Now the problem is, at each point we're going to work out the distance, but once you join 2 points, you've got this little cluster. How do you decide the distance between 2 clusters or between an observation and a cluster? And that's a decision you have to make. You have to say, well, when I have a group of observations, how am I going to have a single distance or dissimilarity measure that compares the 2 clusters? So if you think back to this, once I've joined 24 and 45, the far right, I now need to take them 2 together and compare their distance to all the other observations before I can make the next join. But the whole idea is we're going to start with them all individually. We're going to find the 2 that are closest together, read all our calculations for a distance, find the next 2 that are closest together, join them, find, and every point we have to recalculate the distances, because when we join together now, each cluster is not a single observation, it's multiple observations. So just to show you what that means in terms of distances, what I've done is, if we go back to this dendrogram, I found the point that was on the farthest left, which is 55, and the point which is on the farthest right, 45. Now these are very far apart on the dendrogram, and I've just illustrated on the picture, you can see they're quite far apart when you look at your 2 predictors. So you can see this sort of relationship between your distance on your predictors will give you a separation into different clades, and it'll be a long time before you join on your dendrogram. So you can do cutting. So here, you can either cut by saying, I will choose a certain height. So here, I could have said, I want you to have cluster things together that are a distance of 5 or less. So in this case, you get these 3 rectangles, these 3 clades you could use as your clustering. Or you can actually just say, look, I think we need 3. And often what you will do is you'll produce one of these and you'll look at it and look at the general structure and decide on the grouping. This one, it doesn't look too bad, although, this looks like some nice clustering. And these are used a lot, especially in phylogenetics.
What happens if you drop your height below one of the observations? Outlier or?
How do you mean below one of the observations?
So if you dropped it down to just under 2, you'd be just below 29, is it, on the far right?
Okay, I see. With that one, you'll see in a second you would just actually push them all down. You do a hang -1, you'd hang them down and do it that way.
Okay.
Or it would push it out to a separate point on its own and you'd treat it as an outgroup.
Yeah.
So how do you actually do it? You start with your n observations and you calculate your n choose 2 pairwise dissimilarities. And you treat each observation its own cluster. And then what you do is you just keep going until you get to the trunk that you'll go, look at the number of clusters you've got, find the 2 that are closest, i.e. they have the smallest dissimilarity, join them, recalculate all your distances, keep going. And that's it. So, how do we compute dissimilarity between clusters? So there's 5 I'll do. The first of all are the classic linkage. First of all, you complete says, if you have 2 clusters, work out the distance between every point in the first cluster and every point in the second cluster and take the maximum distance to represent the distance between them. That's called the complete linkage. The single, again, you compare every single possible distance between the group observation in the first cluster and the observation in the second cluster, and you set it as the smallest distance. The average, calculate every dissimilarity between the 2 clusters, take the average of them. And the centroid, you work out the centroid of the first cluster, the centroid of the second cluster, and you look at the distance between centroids. There's a one that turns up quite a lot, which is called Ward's method. It's now, instead of sort of looking at distances, it's looking at a minimum variance criterion. And it basically, at each step, you find the pair of clusters that leads to the minimum increase in total within cluster variance after merging.
Say that again 5 times quickly.
It's used a lot, and I had to go and look, and it's a bit weird because when you actually look at the help file, they go, well, there's Ward's, and there's Ward's D2. And then there's like a paragraph explaining that you should use Ward's D2 because in search and such, someone did a paper that wasn't quite right, and the implementation of that wasn't the one we used. And you sort of read it and go, why the fuck have you got all this? Like, if it was me, if there's one that's right, just fucking use it and not mention it. Just say, all versions are wrong, this is the one to use. But if you really want to read about it, just go and look at your hclust help file and scroll down and it will go about Ward's D2. And it's going to be annoying because what I often do with this is you try every single method and you look at your trees and say, remember, this is still exploratory data analysis. This is not like modeling where you can start testing going, is it right? Try different things and see if there's a pattern that emerges. Lots of unsupervised learning has that sense of, what? You're just trying a bit of everything and see if it's pretty. But that's unsupervised learning. So things you have to think about when you do this, should you standardize your data or not? Because we know, doing dissimilarity measures, if one thing is measured in millimeters, another thing in kilometers, you get a lot of variability in one scale. That's going to dominate your distance. You've got to decide what your dissimilarity measure is. We'll go through this more next week when we look at MDS and different dissimilarity measures. You've got to decide what linkage you're going to do. And then if you've got your tree, you then have to decide a cutoff point to decide how you're actually going to split it. Once you've got your cut, you can either get your groups directly from your hierarchical clustering, and I'll show you how to do that. But often what people do is they use the tree to decide and say, yes, it looks like there's 4 groups, and then they go and do k-means to get the groups. And again, when you k-means, you have to decide on the numbers of clusters. So let's illustrate with an example with the iris again. So the first thing you have to do is you have to get your distances. There's an object called a distance object. So it doesn't give you just a matrix where each entry is going to be the distance. It gives you a lower triangular matrix. Unfortunately, distance objects you deal with a lot, and they're just horrible and faffy. There is ways of basically coercing it. It's storing it in a memory-friendly way. It's quite fast. So you create your distance. So what I've done is I've created a distance metric from everything except for the species name. And the default one is Euclidean. It also has built in things like Manhattan, Minkowski, I think is the proper way of saying it. You have a Hamming distance in there. There's also a thing called the Canberra distance. There's a whole different sort of distances built in. The standard one is Euclidean, is the one that we normally use. Next week I'll go through some of them in detail. So I've got this distance matrix, and then so we can actually look at it, I've coerced it into a matrix and shown you the first 5. So obviously the diagonals will be 0 because the distance between a point and itself should be 0. Normally this will be symmetric. It doesn't always have to be. There's certain distances or certain, so I shouldn't use distances, I'm not going to. There's certain measures you can have that people will treat as a dissimilarity that won't even have symmetry. Classic one, think about car journeys. If you measured it in time. Sometimes driving from the city to Elizabeth, or from Elizabeth to the city, depending on the time of day, will take different times. They still have the sense of, you know, if you travel from here to here, it's 0, etc., but it's not symmetric. So sometimes you lose the symmetry, but we're not going to look at that. But you can see this is symmetric, and so for example, your top row gives you your distances between the first point and the first point, the first point, the second point, the first point, the third point, etc. So how do you fit your tree? Well, there's a thing called H-cluster, and you give it the distance you've got. So you don't get the data, you give it the distance. And you then tell the method. So here I've done method complete, single, average, centroid, and ward.d2. As I said, if you want to lose an hour of your life, please feel free to read all about ward.d2. Then I won't be the only one. And for each of these, then, I can actually just produce it. So here, what I've done here is you go plot. So you now understand why plot can suddenly do this, because the class will be a H-class object. When you do plot, it's an S3 object, it just spits out this particular plot. You give it your hierarchical cluster tree, and then you can actually add labels. So here I've added labels by saying the iris species. So now I've actually put the labels on there. It's quite nice, it prints things automatically, it tells me that this is complete, it's stored that information in there, it tells me it's a cluster dendrogram, you can see it. Unfortunately, it's hard to see, but you can sort of start to see that example. If you look at the far right clade, and look down, you can see nearly all of them are setosa. You come over to the far left, you get in virginica. So it does seem to be separation when we know the truth. Sometimes you don't want to have the bottom sort of unlined like it is. So there's a command you can put in, which is called hang equals -1, which just lines them all up.
Actually, no, it is because you can see the length of the words. It's really
Yeah,
helpful.
yeah, you can. You still go, is that better? I mean, if you really want to, you can manipulate and you can start. The problem with built-in plot functions is you can't, they don't. ggplot is a horrendous thing to learn, but once you learn, it gives you freedom to do a lot of stuff. This, you can't do a lot of stuff. I thought, I will just color. You know, I will just add some color to them labels. That can't be hard, can it? Notice my labels are not coloured. Because yes, it is that hard.
Did you think about maybe Inkscape as an option?
I actually thought about, there is another package called ggtree, which will take these objects and give you ggplot stuff. But I wanted to show you the default behaviour because a lot of people will just use the straight plot. But you can't add colours. And unfortunately, ggtree does not work for cards. Because I did try and use it for that as well, to make them all nicer. So here is now our different one. Here's our single. And now you get a very different structure, a very different tree. You know, you've gone from, here's our complete, which has quite a nice separation. Here's our single. Now you've definitely just got 2 clades. I would put that as 2 clades. Remember, this is looking at the smallest distance between any 2 clusters as its linkage. Here's now our average one. Again, 2 clades. And I'll show you in a second how you can compare between these. You can grab the information out and compare between them. are centroid. And a lot of these were getting these two clades, which I thought was quite interesting. And then our ward, which isn't separating them that well. It actually got the Setosa quite well with that far left clade.
Haven't they all got Setosa completely on its own?
Yeah.
Yeah, that is just, it's so different from the two.
Yeah, be interesting
Got
to
that
see. Did we have that plot right back at the start? Did I actually plot?
It'll be the green one, though, surely.
I wonder if it's the green one. I wonder if Setosa's the green one, which is why it's separating it nicely, while the other ones it's having difficulty separating. But remember, this is only 2, while all these hierarchical clusterings are using all 4 measurements as well. So next, you can add the rectangles. So there's actually a function, you do your plot, and then you can just go, in this case I went rect h clust, give it the thing, and I say how many rectangles I want, so in this case 3. I believe there's a parameter you can actually give a height instead of just saying I want 3. So you can split it. I'll show you in a second how you can actually then also assign each observation to a cluster using that split. Which is the cut tree. Well, it's not, it's the coup tree. I discovered this because I thought it cuts the tree. I typed cut tree and he went, I don't know that function, Jono. Where did you get that one from? And then I realised that they've called it coup tree.
Or cut rate.
Cut rate. But you can basically say with that, you can say, go and you've got your hierarchical, cut it into 3 clades, label with them 3 clades, and it will just return a vector of the labels. So in this case, that's what I've done. And you can see the final column is which cluster it's in. So then I wanted to look and say, well, how does it do? So what we've got here is I've used a geom jitter. I've coloured by the actual species. So you've got everything that was clustered as 1, 2, or 3. So if we go to the first column, all them points to the bottom, that's the Setosa one. That's completely separated. The red is done really well. Cluster 1 is all Setosa, only Setosa, which is good. If you go to cluster 3, so you go to the right hand side, you see that's doing pretty well as well. That is all our versicolor. But obviously it's got one of the Virginica wrong. The problem is at cluster 2. At cluster 2 is basically about almost 50-50 when it comes to the 2 species. So it's not done too bad, but it's not brilliant. Then I just did a k-means. So I've got my hierarchical clustering, I've got my k-means, and now I'm comparing how they both do. So you can see, for example, with the k-means, it called it cluster 2. Remember, there's no sense of what these numbers are, it just gives it a cluster. But its cluster 2 on the k-means is completely mapped with the hierarchical clustering cluster 1, and it's getting all of them. You find that the k-means is doing not too bad when it comes to the Virginica, but you do find that it finds it very hard to separate the versicolor and the Virginica. That's it. Oh, that's not too bad. Any questions? So that's k-means and hierarchical clustering. Next week, MDS EM algorithm. After that, we've probably got MapReduce, and then that might be all the context for this course. And we might do some almost workshop type things within the lectures. Unless there's something I've not covered you really think must absolutely be covered. Is there anything you've heard about that you think I really would like that in there? Anything? No? Nothing?
The neural network stuff is pretty cool, was probably too.
I can have a look at it.
Yeah.
I can see if I can find something on neural networks. Anything else? So we've got a vote for neural networks. Cool. That's really good. So, you have an assignment due this week? Is that right?
No.
So you got assignment due. The votes are up. It looks. I'll check again, but it looks like everyone's voted for week 12.
Because we don't want to be bashed by the rest of the class.
What?
If you vote for the
You're the only one who's not voted. Everyone else I checked have voted. Like when I checked last night, you're the one who hadn't voted.
What did you expect, John?
If you voted,
Huh?
we
What did you expect?
I don't know, because some people just like get it over and done with.
Yeah, but they can still hand it up on the.
Yeah, they can-
Yeah.
Is the thing.
But alright. I'm happy to do week 12.
Does it have to be unanimous? Like, do we have to?
No.
You know, steal
No, it has to be a
vote,
majority.
vote?
I thought I voted.
Has to be a majority, that's all.
Sweet.
So,
I'm happy to get the later one.
I'm happy to give you an extra week. Doesn't bother- the only reason I thought about moving it was I suddenly realised that your presentation, your assignment on the same day, and I know that some students cannot even make my lecture, and how good is this, and do an assignment on the same day. So I'm worried that that puts too much pressure on. So I thought, split it.
My not attending lectures independent of the science review.
Oh, you don't just attend lectures because it's fake. It's like, I'm sure I can predict it,
Immediate.
but it's going to need hardcore machinery than this.
Very stochastic.
Very stochastic. Any questions at all? Cool. See you all. We have done a workshop this week. See you all Monday when we do MDS. Workshop next week will be how to write package in an hour. I tried it yesterday. I did it in 45 minutes. Uploaded on GitHub, works.
What does it do?
Like 15 years before you do that.
Yeah. No, first time, my first package took me a week, but I'm not going to tell things like that. Cool. If you have any problems, come and see me. Remember, today's my busy one. Today's less busy if you're trying to catch me in the office. Thank you all.
Or not.